I know the vertical components are all gonna cancel out, and we're left with just the horizontal, which will get weaker and weaker and weaker. But with electric potential, there's no canceling out at all. It's just one compounded onto the other, and it just happens to be,
Wouldn't it reach a limit though of where it wasn't really adding anything else to the potential? Because
Yeah,
it's
but
getting farther and farther away.
but the other part of that, it's decaying at a rate that will not give it a limit. It, as you get farther and farther away, it's contributing less and less, yes, but not fast enough for it to eventually hit its own asymptote.
So like even though it keeps adding tinier and tinier amounts, it's still adding amounts, therefore you still call it like infinite potential.
Yeah, but just the way it works out. Unlike electric field, where it is also getting weaker and weaker as you go, but it's an over R squared instead of R, so it's gonna drop off faster than just R. And also you're losing little bits of it each time as you go farther out. And I don't know if I mentioned this before, I mean, whether it's having the 1/R squared relationship is incredibly convenient for a lot of things. There's going to be another point in there, lost. Other questions? All right, so our big four quantities: electric force, the electric field, the electric potential energy, the electric potential. We have ways of combining them, but let's take a look at one. Let's take a look at one other relationship here. So if I have the force, I can do force divided by by one of the charges, and I get the electric field. Going over to potential energy, well, I know that potential energy is the negative integral of F dot dr, whatever letter you're using for position. And if I divide by a charge, so delta U divided by Q, I get delta V. So delta V must be the negative integral of force divided by whatever charge that is. I guess I should stick with capital Q there, over capital Q dot dr. And that's just the electric field. So I have my voltage is the negative integral of E dot dr. If that's true, then my electric field also equals negative dV dr. I think that's close enough now. If I'm dealing in one dimension, yeah, we'll just can't wait for that one. Using the traditional I hat with positive x direction, we have this relationship here. But if I'm dealing with two dimensions, well, then there's another piece, dV dx. J hat, or another one, dV dz. k hat. And actually, as you're going through this, these are regular derivatives, but it turns out it's actually related to a partial derivative. Now, in one dimension, we're not gonna notice much difference, but when we get to multiple dimensions, it might. So technically, hand wave, it's negative del v del x I hat minus del v del y j hat minus del v del z k hat. Now, memory is that some of you have done partial derivatives. It's at the end of Calc 3.
No, it's like in the middle.
Yeah, we're doing them right now.
Oh, okay.
Like you were talking about gradient the other day, like,
Yeah, we literally.
that night, we talked about gradient in calculus.
It's fate. So as I'm looking at that, then I can also just write this as, in essence, it's gonna look like I'm factoring V out. It's a little bit different than that, but the del x, let's take the I hat up front, because otherwise it looks like I'm doing a partial derivative of I hat minus j hat del y minus k hat del z times v. Now, in a situation like this, we've got v kind of factored out, but the notation is that I'm basically, this does not exist by itself. This only exists to operate on v, so this is a vector operator.
Oh, those are all portions, or I was thinking those are two.
And those are all partial derivatives. Now, partial derivatives mechanically are incredibly simple, or they're simpler than regular derivatives. If I have v is equal to 5xz minus 4y squared, if that's the equation that's going to describe my electric potential, then I can find my electric field by just doing my partial derivatives over there. So when you do a partial derivative, so dv dx, is you assume anything that is not an x is a constant. If you're doing a regular derivative, you have to pay attention to how y and z are affected by x. How, are they functions of x? But in a partial derivative, you don't. So del v del x would just be 5z. Del v del y would be negative 8y. Del v minus 2 del z would be 5x. So my electric field is going to be negative 5z I hat minus 8y j hat plus 8y j hat minus 5x k hat.
Is the partial derivative symbol a delta, like a lowercase delta or something? Why do you keep saying del?
That is what my memory is of what my professor called it.
Hmm.
But there, because the
I was just
lowercase,
curious.
I think the lowercase delta was more like that.
I was just curious why you're calling them del.
To differentiate from D. The electric field is a vector. Now, this whole vector operator over there, that just gets too much to write. So of course, we come up with a symbol for it. Actually, I can factor the negative out, so I've got negative I hat del x plus j hat del y plus k hat del z times v. This right here it's a vector operator, so it only exists as it operates on something, and we end up with that is the symbol, that is the nav one. I think I mentioned it the last time we met.
That symbolizes gradient.
It symbolizes this right here, it's a gradient if it is operating on a scalar. So we have the electric field is equal to the negative, because that's operating on a scalar here, that would be the gradient, so it's the negative gradient of V. So we have now connected the relationship between these two. The fact that, well, circle. However, let's take a look at a special case. Let's assume that the electric field is constant. If the electric field is constant, and I'm going to assume that, well, no, I won't make that assumption. Never mind. All right, so electric field is constant in space. Not commenting about whether it changes in time, but if it changes in one part, it changes everywhere. I know that delta V is the integral, negative integral of E dot dr dx, whatever letter we're using. If E is constant, it can come out, I'm left with negative integral of negative E dot integral of dr, which is just R. I guess from limits of integration from R initial to R final. So that's negative E dot R final minus R initial. In other words, negative E dot delta R. So if I have a situation where I have a constant electric field, then I can find my potential difference just by multiplying electric field times my displacement. It is a dot product, it's how much is in line with the other. So if I have an electric field going across like this, uniform, and I go and I move from here to here, so I move to the right in the direction of the electric field, I know that my electric potential difference is going to be negative. Because if I move in the same direction as my electric field, that is going to be a positive number, then negative suddenly switches the signs. And so my electric field is traveling to a lower potential, which matches stuff that we talked about earlier. So if I'm going in that direction, my change in potential is negative. So if this is an infinite sheet of charge, with uniform charge distribution, surface charge distribution, sigma, where sigma is 5 microcoulombs per square meter. And I am here, say say a distance of 3 meters away, and then I go to here. So I'm now 8 meters away. So as I move from that place, from the first spot to the second spot, I'm going to undergo a change in electric potential, and we can now calculate it. Because I know if I have an infinite sheet of charge with a uniform surface charge distribution, my electric field is constant. Matter of fact, my electric field all along here is sigma over 2 epsilon sub naught. If that is my charge distribution, it is constant, and so it is in the direction of movement, and so the change in potential would be the negative of my electric field, sigma over 2 epsilon sub naught, times how far I went, times delta x, which is negative 5 times 10 to the negative 6 coulombs per square meter, over 2 times 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared, times 5 meters. Go through the fancy math and you end up with an answer in what will be Newton meters per coulomb, which is a joule per coulomb, which is just a volt. Yeah, I probably could have picked more convenient numbers.
Is that 2 over the epsilon sub naught?
That's sigma over 2 epsilon sub naught.
Okay.
2 epsilon sub naught is the denominator. So that's a simple case, and this will come back in chapter 27. Let's do something a little bit more mundane, but still involve a little bit of calculus. I have a sphere of charge. Conducting sphere of charge with an excess charge of, say, 5 microcoulombs. Let's give it a radius of 0.15 meters. And I want to know what is the electric field? Let's plot the electric field versus R distance. Since that, we'll make that a capital R there. All right, I have a conducting sphere of charge. I have an excess charge distribution on it. What do we know about the charges?
They spread out evenly
Okay, where?
on the surface.
Okay, and if I'm outside that,
You can treat it as point charges.
singular.
Singular.
So we treat it as a point charge centered right there. So if I'm out here, what is the relationship? Or what's the formula?
KQ over R squared. R hat.
And so it's going to have whatever R squared relationship is going to look something like that. Suppose I'm inside.
It'd be
0.
Assuming that the charges have moved into electrostatic equilibrium, it would be 0. Presumably simple enough. Now let's plot again, if I'm outside, I'm gonna treat it like it's a point charge. What is the formula for electric potential, assuming the constant is 0? Did you announce?
KQ over R.
Yeah. So it's gonna be a 1/R relationship. I guess relatively speaking, this should not be as quick a dip as this one is. If I'm inside, what do we know about the electric potential?
Would also be 0.
It's
It does
constant.
not.
Same no matter where it is.
It's constant. If we look back over here, it's a one-dimensional problem. In a one-dimensional problem, I have only one variable, so the partial derivative and the regular derivative are the same. So it's gonna be the negative of, so the electric field is just the negative of r hat of the slope of v. So in terms of the relationship, I know that the slope of v here is 0, the electric field is 0. The slope here is negative, so my electric field is the negative of the slope. So if my slope is negative here, my electric field is positive. The fact that this is 1/R becomes 1/R squared, this is calculus. So we now have a way of actually, if we know one, we know the other. And